So hello everyone, I welcome you in my class. So in today's class, we will discuss on a static stability part in little bit more details. That means we will consider the wing positions, fuselage, power plant, landing gear and canard. That means how it will affect the aircraft static stability. We have seen how the wing and tail affects, right? So in this lecture we will see how the wing position, fuselage and power plant, and in power plant also pusher, tractor, and if there is some kind of CG offset is there, then what will happen, and then landing gear, and then finally canard, which is forward tail surface. Okay. So we know that for a to achieve the static stability, the Cm alpha should be negative. Okay, let's build some little bit theory here. Okay, we have seen already. So let's say this is a airfoil. In general, we draw the cambered airfoil. Okay, from this airfoil, the wing is made. So we have drawn just the cross section. Okay. So let's say lift is acting at a C by 4 line. Okay, this is C by 4 line, and CG is somewhere here. Okay. So if I mark this as a XCG, and this is a aerodynamic center, so this will be the XAC. So and this point is leading edge. So I can write the moment about CG like this: moment about CG L into XCG minus XAC, right? Moment we can write half rho V square S C bar. And lift we can write half rho V square S CL, and this is XCG minus XAC. Half rho V square is a dynamic pressure, where rho is the density, V is the aircraft velocity. Okay, S is the wing area and C is the mean aerodynamic core, and CL is a lift coefficient. So we can write and into Cm. Okay, so Cm is a pitching moment coefficient. So we can write Cl equal to XCG minus XAC divided by C bar C. Okay, we can further Cm we can break Cm naught, Cm alpha into alpha. Okay, and that Cl we can break Cl naught, Cl alpha into alpha, and this is XCG by C bar, XAC by C bar. Okay, so here I can write, if I compare Cm naught, okay, so Cm naught will be, if I compare left hand side and right hand side, we will get XCG by C bar, XAC by C bar. And what is Cm alpha? Cl alpha, XCG by C bar, XAC by C bar. Okay, so this Cm naught tells you that you can fly at a positive angle of attack, or you can trim the aircraft at a positive angle of attack or not. If Cm naught is positive, that means you can trim the aircraft at a positive angle of attack. That is not very necessary condition for a to make a aircraft stable, and this Cm alpha is a necessary condition in order to make a static stable flight. So how will you achieve this Cm alpha negative? Okay, that means why Cm alpha negative? Let's say aircraft is flying and you have some angle of attack alpha. If you increase the angle of attack alpha, then aircraft has a tendency to pitch down itself. That is how you will counter, right? So that means Cm alpha should be negative. If you draw the curve, this will be look like this. This is Cm, this is alpha, this portion is Cm naught. Okay, that means here if you are flying any particular trim point, and if you increase alpha, okay, so that means if you increase the alpha, that lift will increase. Okay, so lift will increase, and if CG is ahead of the aerodynamic center, then what will happen? there will be nose down moment. That means this moment will be less than compared to the this moment. So when you increase the alpha, right? And how it is coming, you can see from this graph also. So in this case, if the angle of attack, let's say this is a chord and this is angle of attack. If angle of attack increases, lift will increase. Is a destabilizing configuration. But when you put the CG here, that means this distance will become negative, and that is how you will achieve the stable condition. So from this expression, one can easily say for a static stable flight, CG should be ahead of the aerodynamic center. Okay, but wing alone configuration is generally not possible. Okay, and even for a wing alone configuration, what you can do, you can put AC behind the CG by taking the sweep back. Okay, or what you can do, you can put a tail. Okay, and you can stabilize the aircraft. So that is a condition. That means CG should be ahead of the aerodynamic center. All right. Okay, so from this graph we have seen. So okay, so whether you will place the high wing configuration, low wing configuration, or mid wing configuration, this criteria should meet. Okay, so I mean to say that ki wing position generally does not affect more on static longitudinal stability. However, when I will teach you the aircraft lateral stability and directional stability, then you will see the low wing and high wing configuration plays a very major role in a roll stability and directional stability as well. Okay, although for a high wing case, one can say that there will be, when you increase the angle of attack, there will be more exposed area of a, what you can see, wing. So that means there will be increase and drag, so that will try to further pitch up the aircraft. That comment you can actually make. And when we see the high wing configuration or low wing configuration, consider this a high wing configuration. So it is something you can see inverted pendulum type. So that means laterally it will be giving the stability. I will discuss it more in detail. So from this math we have seen that what is the importance of CG position actually. So as far as the fuselage part is concerned, we will see the fuselage thing part. Okay. Generally, what is the shape of fuselage? You will have this kind of fuselage shape, right? This kind of generally. Okay. So you can break into the three sections. This section, and this section. So this section is generally, you can see this is a rectangular thing, you can see, and aerodynamically if you draw this section, it will look like something like this. And this is a center section, and this is a lower section. Okay. So when you place this fuselage at angle of attack alpha, so what is the tendency? Lift will increase. This shape will provide the more lift than compared to this shape and this shape. Okay, aerodynamically. So if let's say CG is somewhere here, let's say I can mark this CG location is here, this side. Okay, this side. So what is the tendency for a positive alpha? Positive moment, right? So that means CM alpha is greater than 0. So clearly you can comment on this part is destabilizing, this shape. Okay, and what about this? This shape will provide the negative lift. So again no sub moment. So this is also, the contribution is also providing the same alpha greater than 0. Consider this is a central part, does not provide much on a stability side and all, because this you can see for a small angle of attack this will not produce any lift. So there is no meaning of talking about the stability part considering the central part. Okay, you can clearly see that fuselage is a destabilizing component. Okay, so wing alone is also destabilizing, fuselage is also destabilizing, although for a wing case if you give the sweep back, the sim will take the aerodynamic center behind the CG, you can make the stable. So you can see, but tail is a horizontal tail is a stabilizing component. You see, we have seen already, right? So that is the importance of tail design in an aircraft. Okay, in order to make overall aircraft stable. And consider this power plant part. Okay, so we'll consider the power plant part. So there is a two type of configuration. Okay, let's say if this is a fuselage, if you put the propeller this side, okay, this is called tractor type. Okay, and when you put the propeller this side, this is called pusher side. So you can see when you and CG somewhere else. So when you put uh, tractor type, sorry, pusher type here and tractor type here, so what you are doing in this case, you are taking the CG back because due to this weight of the power plant, and in this case you are taking the CG forward. Okay, you can comment on using this. See, static margin is nothing but distance between neutral difference between neutral point and XCG. That means, let's say this aerodynamic sector we have put na for a wing. For a complete aircraft, we will replace this point by the neutral point. Okay, so when you put the tail, the neutral point will be somewhere here. Let's say, so the distance between neutral point and XCG, okay, from the any reference or wing leading edge or fuselage nose part, this difference is called static margin. So if this is a neutral point, let's say after putting the tail, and this is a CG, so when you are putting the pusher type power plant, that means you are taking the CG back. Okay, so that means what? You are reducing the static margin. So actually the stability will go down in case of pusher type, but in the case of tractor type, this CG will move forward. So that means you will get more stability. So that means more control is required in a tractor side and less control is required in a pusher side when you want to change the pitch angle or angle of attack of a aircraft. So that means I want to stabilize the stability and control relation as well. That means if the aircraft is more stable, okay, that means more control is required. If less stable, less control is required in order to navigate the aircraft. Okay, so you can see how the pusher type and tractor type plays a very important role in terms of static stability. There is a CG offset, you have to also consider this point. For example, if CG is this, and if the thrust line is, let's say this is the thrust line produced by the engine, if it is passing through the CG, then when you change the thrust setting, there will be no change in what you can say uh, pitching moment. Okay, so when you change this, I am talking about the control perspective here. Okay, when you change this offset, that means there is some kind of offset, and when you change the thrust setting, there will be pitch up movement, right? So you have to counter that. Okay, so that means if there is a CG offset is there, then there will be you can see even the this curve, from this curve you can see CM naught plus CM alpha into alpha. So when you take the moment about the CG, although this is independent of alpha, but it will contribute towards the CM naught part. So I want to say, although it is not included in the CM alpha part directly to the stability, but there is a this will affect the CM naught part. Okay, so that means when you increase the thrust, and if the CG is above the thrust line, so it will produce what? Pitch up moment. And similarly, if the thrust line is this, so it will be pitch down moment. So accordingly, you have to deflect the elevator in order to counter this. So you will see there is a change in CM naught when you put this thrust. So in extra topic, what I will do, I will try to cover more in detail with the derivation as well. Similarly, in a landing gear case, for example, if there is a landing gear this side or this side, if the aircraft is flying and if there is a more speed, so what you can see, if there is a offset from the CG, so drag direction will be this, that will try to again produce the pitch down moment at the CG is above the drag line, that means landing gear drag line. Okay, so again there will be, you will see the change in CM0. Accordingly, you will have to make a elevator setting in order to counter the additional moment provided by the landing gear. And you have seen that key, there is, for a highly maneuverable aircraft, you want to increase the maneuverability. So what you can put extra control surface front side of, okay, of a fuselage. So if you put this kind of surface similar to like a small wing this side, okay, so that configuration is called Canard configuration. So this configuration will provide both lift as well as a control. So actually what you can do, you can shift the neutral point from this side to this side. So if your aircraft, if you want to make a more maneuverable aircraft, you can put a canard over fuselage front part, which will provide both lift as well as control. So there can be all movable canard or partially movable canard. Okay. So next topic we will discuss more in detail how the canard will affects the total lift and total control. Okay. So thank you so much.